like that. All right. Hello, everyone. We're going to start number 3 in our series here. Again, talking about intelligence and cybersecurity as an analyst apprentice approach and viewpoint. This one's actually going to build on DNS, domain name system, like we talked about in the previous one, but we're going to talk about a little bit different parts of the DNS that we normally don't focus on. But hopefully by the end of this presentation, you're going to understand why I want you to know it really, really well, because you're going to see what we can achieve as analysts by having a fundamental understanding of some of the very large strategic pieces of DNS. Things that often get overlooked, but contain very crucial elements of intelligence that we can glean to understand our adversary. It's kind of why it says straight to the backbone, because we're going to talk about those very large parts of DNS. I'm going to click the wrong button. There we go. Here's my ugly, ugly picture of the internet. It is indeed a network of networks. And that's kind of important because you need to understand that a corporate network is one of these networks. A network that belongs to an internet service provider is another one, and they all kind of come together. It's just not as seamless as you might think. It's a little more kludgy and kind of old-fashioned in some ways than you might expect. And like the picture kind of talks about, there are large, like those larger colored in bubbles indicate very large kind of networks. And you see there's lots of subnetworks that are descendant from them, and they have things both upstream and downstream, things that I'll kind of talk about here in a bit. And that's logically the DNS backbone. Now I'm going to say up front, there is a difference between the physical topology of what we consider the internet and the logical topology. I'm really talking about more the logical structuring than I am the physical. So we're not going to talk about trunk lines and where they're buried and how they go under the ocean. That's the physical topology. There's some interesting analysis that can be done there, but it's not really for the cyber field. We're looking at the logical way this all comes together, and it doesn't match. It doesn't like evenly lay over one another. They are very, very widely different in some, and not some, but like almost every instance. All right, so I want to start with a very, very important, very large, strategic, and broad swath kind of topic, and that is an autonomous system. We also call them ASs or AS numbers, right? Now, I'm not going to read all the bullets here. You can read as well, but if you look at my globe here that I borrowed from a website that did a really nice job of showing this, ASs are kind of all over the world. And there's a rhythm and a reason behind their naming convention, which I'll touch on here in a second, but it doesn't match up. Like, you're not going to find all the ASs that start with 612 all in the US. They're actually going to be spread out all across the world. Think of it as a one-up system. The next AS that shows up gets the next number. And depending on business cases, the agency that issues those numbers so that they get recognized might skip like 10 numbers and then give them number 11. It's really up to them. The key thing that we need to remember is those numbers equate to a block or a large network that is part of the internet and is part of a unified routing system. So when we talk about packets, which are bundles of data moving around the internet, kind of everybody knows that that's how the internet works, right? That these packages of data kind of float around, pick the best path, and try to get you where you're going. Well, they do that by navigating between different autonomous systems. And most of the autonomous systems are kind of big blocks of computers or logical things that resemble computers that are grouped together for a particular reason, usually a business reason, sometimes a geographic reason. And absolutely everything that is in the internet is connected to one or more ASs. There's no way you can have an IP address of any kind and not be inside of one or more autonomous systems. That's very, very important to remember. Now, the number, as I mentioned, is kind of provided, and the first paragraph here talks about what that is. And it's meant so that whatever block of computers you represent can be rendered in a way that's easily identifiable in text and can be understood at a global way and can be used to exchange routing information, like how one AS talks to the other. And I've got a second bit here about how the numbers are created. And you can see they're between 1 and 65,534, or they're a 32-bit number. Now, kudos for anybody who can tell me why there's a cap at 65,534.
Is it like a buffering thing? Like,
Pretty close. It is because of a limitation of some kind, but it's not necessarily a buffer limitation. I'm looking for a specific way to describe it.
Isn't it a binary thing?
Well, binary is basically by definition, one is 1 and 0 kind of situation. So not quite,
Fair.
but you are kind of going, both of you are kind of going the right direction. It is because of a variable cap. There is an allocation of memory there in the early days where 65,535 was the cap.
so it's like based on the old school tech. That was the limitations at the time.
Yep. And that 32-bit number sequence is the innovation that came afterwards.
Oh, like the IPv4, IPv6 distinction kind of thing?
Yes, exactly. So by that alone, as an analyst, your brain should go, huh, really old ASs probably have a number between 1 and 65,534. And some of the more recent ones might have a 32-bit number instead. I would hope your brain would go there immediately, because that would be a truism. Though you can have a brand new AS that has a 16-bit number. It's more than possible. It's all dependent on when they get assigned. And it's important to understand that ASs aren't static. These large blobs of computers that kind of are networked together, they come and go. In the minute or two we've been talking, several of them have disappeared from the internet forever, and new ones have taken their place. It's that quick and that transient. Some are very static, don't seem to change. Some come and go very rapidly. And nobody talked about this yet, but I'm going to bring it up anyway. I kind of did these a little out of order because I was thinking about various things when I was kind of constructing this. So I'm going to take a step here and say BGP stands for Border Gateway Protocol. When I talked about earlier that there are these large autonomous systems and there's routing in between them, the routing is called Border Gateway Protocol. And it has its naming because the borders where ASs touch create two borders that make a gateway. And the protocol in which they talk on is what we're referring to. So I want to make sure that is very clear. And also that autonomous systems belong to things like ISPs, large organizations, tech companies, universities, government agencies, scientific institutions, and so on. They also belong to companies. It depends. You can buy basically an AS if you have enough money and it's available. The thing that is required for the internet to say you exist and that they're willing to route traffic to you is you have to be registered. And that's where that number comes in. You have to have a number. And there's one agency in the entire world who governs that. And that's IANA, also known as IANA. It's the one that assigns ASNs. Now there's another thing in there called Regional Internet Registries, or RIRs. And there's roughly 5 or 7 of those. I say 5 to 7 because it seems like there's 5 core and then 1 or 2 that come and go. Just depends on politics a little bit there. But there's a bunch of these. And you know them. LACNIC, for example, is a RAR. That's Latin America's version that handles basically internet for the Latin American area. AFNIC handles Africa and so on. It has that kind of nomenclature. And they're the ones who actually lease the ability from IANA to be able to give AS numbers to large blocks of computers that are going to be routing for the internet. And I'm going to talk about routing. So you may have questions about it right now. Just hold on just another few slides because I'll explain why routing is important. But the biggest thing I want you to understand right now is any computer that's on the internet with an IP address is in an AS. And it will have routing data connected to it. And that's important because, as I talked about in the previous slide deck, as analysts, we need to know where all the artifacts may or may not be, because every action will create an artifact. It will leave an artifact behind or it'll create one. And we need to know that because if we're looking at someone's activity on the internet, say attacking our company or doing something that we want to track down, knowing that the pathways are all going to leave a trail of artifacts gives us breadcrumbs to follow. Knowing how those interactions occur help us dig into areas where there might be even more artifacts that can let us understand what happened better, or even identify the person who's performing the action. But more on that later. Let's stay broad strokes. I'm going to tease a little bit and say that we're going to get to be able to do those things. So core part of the routing is the routing policy. And this is very simply a text list more than anything else that addresses what IPs an AS controls and who that AS is connected to. If you think about that idea that a packet of data will travel the internet moving from one AS to another, it's kind of important to understand who's connected to whom and who handles one particular IP over another. Otherwise, you can't route properly. And as I said, I kind of got my slides a little out of order, but yeah, that's border gateway protocol. That's actually a protocol kind of, and we haven't touched on these, but it has its own way of announcing and accepting information. And it does it through the internet in a particular format that we can identify as BGP. And it is something that can be easily gotten and tracked. And we do. Now, here's my promise about how just a very naive, simplified view of how packets would move and how ASs interact with each other. If you look at my diagram, I want you to, first, before you go down the road here, understand that BGP and ASs are kind of like the postal service of the internet. Kind of like how you would pick up a letter and put an address on it and submit it to someone. BGP kind of does some of the similar actions, right? Unlike your postal worker, though, it tries to find the most efficient path. And so given an even kind of environment in which to work in, they would go in using the model starting at AS1, and they were trying to get to AS3, they would go AS1, AS2, AS3, because it's the shortest path with the least amount of problems over going hop, hop, hop through AS6, 5, 4 to get to 3. Like I said, in a kind of even world, no problems, no business, no business arguments, no political boundaries, none of that kind of stuff. It would work seamlessly and beautifully this way. Unfortunately, that went a little close to the bottom. It's a little more complicated than that, mainly because the AS2 route might look logically the simplest, but might be the most complex and take the most time because of business cases. That could be a country or an entity that says, no, for political reasons, I'm not going to route traffic from AS1. Or they might say, hey, AS1, I'll route traffic for you, but you got to pay me. And so AS1 might choose a route that goes through 654 to get to 3 for that reason. And that kind of becomes important because something that attackers fail to consider is this fact. They forget this. And it's something that we can watch that can help us understand and select key information to understand their activities, operations, and who they are. For example, if I am a bad guy and I want to set up some attack infrastructure and I'm like, it's cheap to buy space in another country, let's say Singapore, they've got great data centers, or maybe Vietnam, they got great data centers. I grab some data center space, I throw some VMs up there, I harden them against being detected. I put proxies in between me and those VMs and the VMs and the attack I'm about to do, thinking, aha, I've protected myself. Forgetting, though, that because of the real world situation I semi-described here with business cases, there may only be one or two paths that data leaving that data center can take. And there will definitely be a choke point where everything kind of comes together. From a nation level, as a nation, we might put a sensor there to understand things properly. And then kind of have this man in the middle approach. As researchers and in the commercial sector, that's less likely, though there are plenty of those present that one company or another supports that you can take advantage of. The Sonar project, for example, from Rapid7 has sensors all over the internet that does exactly that, lets you see data on this kind of traffic. And you can ingest that and kind of understand routing. And there are plenty of other tools that we use that lets us understand how one IP interacts with and what path they've taken. Again, all these ASs kind of interacting with each other. And so to kind of simplify this just a little bit more, if you leave the door of your house, if you look at the door of your house, and you're like, if I left my door right now, how many paths could I take to get to the road that's right outside? For many of us, that means leaving our door and either going down the driveway or crossing the lawn. There's not really a lot more options, right? You could do some crazy things, but I don't see us teleporting anytime soon, at least without some major technology upgrades. And so that helps us understand if you can't walk across the lawn because you just seeded it and you don't want to destroy the things you put down, your path is going to be the driveway. Now, if I'm sitting there watching with a camera, everybody who transits the driveway, I'm going to see you every time. And so you can kind of leverage this as analysts if you can get the right insight and the right sensors in place to really understand how people operate. And I really want to drive this home. We're going to talk about a little bit more about how that happens. But as analysts, a common misunderstanding that I combat when I talk to people is they feel there's no way to predict anything. Like everything just seems to happen. There's no way you can see it coming or make a prediction of what may or may not occur. And that the attacker's advantage is so overwhelming that you can never see when they're going to strike. I combat those two problems all the time. And the reality is with this level of understanding combined with a few other very high level concepts, you can push back on both of those wrong understandings. What they really need to understand is with the right insight, with the right intelligence program, you can do good predictions. You will still miss because nobody predicts 100%. We can't see the future, but we can get the shape and understand the process of how things are going to develop and frequently get very close or be in the ballpark of what we need. And at the same time, the paths become very visible if you can see the few possible ways that something could shape. In this case, we're talking hops of data that may, you can translate that up into a stream of information or a connection between that data center and the person you're trying to protect and understand what it took for them to get there. And then get timestamps and other things that can help you really dig into detail. But I'm going way, way too much farther than I need to. But continuing on to that, the key thing that's on the previous slide that I want to go back to is that second statement there. There are hundreds of thousands of asynchronous systems. Autonomous systems. And that hop count is kind of only part of the bigger algorithm on why one path gets selected over another. But it's an important one. And hop counts themselves are a part of defense and offense. As a brief side that's kind of relevant, inside of your enterprise network, it's very, very normal for you to have a hop count of about 7 hops or less, in many cases, even 5 hops or less to reach anything inside your enterprise network, no matter how complex. You have a few instances where you may have hops that go farther, and a hop is defined either by transiting a autonomous system in the internet or inside your network moving to one router to another router, because inside of each one of these autonomous systems is basically a glorified router that is being transited and counted. And each packet that is built inside of it, the very packet structure has a hop count function that you cannot turn off. You can only step on it or change it. And doing so is very obvious when you do it. So with that in mind, moving on to this next one, know that those autonomous systems are always changing. As I said, in the amount of time we've talked so far, probably hundreds of new ASs have shown up and hundreds of old ones have disappeared. If you think about that, that means every AS, all those hundreds of thousands, have to be kept up to date with the information about these routes, as well as routes that are no longer present. So when you look later on and we do interactive portions of this, and we're looking at through what they call a looking glass, which is staring at the internet through a scope, and you're like, oh, this says they dropped a route and now there's a new route being announced. That's what they mean about a new route has been brought into being and an old route has been dropped. And that has to percolate out, because if you know it, but your neighbors don't know it, they will route the wrong things to you because you haven't updated them. So it's important that you communicate in all ways you're connected to someone that you've had a change of routing. And that kind of encompasses their number 3 there. I'm going to do one more slide, or maybe one more slide, and then I'm going to pause for a second to let you get some questions in. This goes back to me talking about the different paths. Our postal system analogy falls apart really quick, right? Instead of having addresses and paths, it gets worse because ASs are sometimes in competition and they fight with each other. And that really can make routing a struggle and really factor in. So let me pause in case there's questions, because we talked about some big concepts that I really want you to hold on to.
Okay, so it sounds like border gateway protocol in and of itself could probably be like its own course, right? It sounds like it's insanely complex.
But it isn't. I'm going to show you what it looks like here in a minute. And
okay.
In and of itself, what you see is not complex. How much it covers is like it covers the whole world. So it's big, but it's all text, right? The concept is what you need to understand, that every AS is got computers in it, and every computer that's out there is inside of an AS somewhere. And that by itself means there's a door that anybody entering and exiting that AS has to walk through. And that door has a sentry on it, and they mark down people that enter and exit. It's part of the artifacts that get created when you move through the internet. Many of those, though, are transient. They only exist for a certain amount of time, and then they get moved because there's only so much buffer, using your word earlier, there's only so much room for them to keep track of things. They keep track of enough and then not any more than that. So they're constantly dropping off data. But if you know this is happening, you can actually watch what's going on. There's plenty of tools that will do this. And again, we get in the interactive part of things. You'll see this. Anybody that's used NS lookup or its equivalent has watched a packet transit the internet. Those are it transiting through those doorways in different ASs.
Okay, that's a lot easier to picture.
Well, speaking of pictures, so here's a real one. So that AS 11427 is a Comcast, Austin Comcast AS. And it contains a lot of IPs, a couple thousand. And this right here is its diagram. So it's announcing to everybody around it, hey, I take care of whatever, whatever. There's notation that we're going to get into next to talk about IPs, but a grouping of IPs. That AS 11427, that farthest left one, it's always going, hey, I take care of, and it lists out its IPs. And in this diagram, that bigger arrow between 11427 and the one right across from it, 7843, is just this graph indicating that that's the preferred path for it right now. At this moment, when I took this snapshot, that was the preferred path.
Well, it looks like there's like a flow to it, right?
There is.
Do they communicate the other way as well, or?
Oh yeah. So good question, leads into this one. Let's talk about upstream and downstream. Now this is going to be confusing. So for me, I always look left to right, and I'm like, okay, downstream must be everything to the right. Well, it's the exact opposite. So just flip it in your head. That's what I usually do to make sure I don't forget it. So if you look at my explanation on the right, so that 11427, it relies on 7843 and 2115 for routing. So packets that come to it have to go through either one of those ASs. So unless it's routing internally, any external packets are going to transit those two ASs next to it. And it's always announcing what it cares for. And those two are always announcing to it who it cares for, what IPs they take care of. So that means they're considered upstream. So 7843 is upstream from 11427. Like I said, for me, I have to flip it in my head. And it's the exact opposite. 11427 is downstream for 7843. Don't get too caught up on this. We don't usually talk about this all the time, but it's just the way the flow works. They kind of depict it one way, but we think the opposite, at least I do. So let's do that kind of real life-ish. Oh, before I do that, this is more on upstream, downstream. So can think of it, anybody upstream is a transit peer, so someone you have to pass through in order to get to the internet. So if your IP is here, right, to get to the internet, you might have to go this direction. If you're here, you might have to go this direction. It's the biggest thing you need to kind of remember. That's the point of all these. Remember, each one of these has got a little door. You got to pass through it to go here, and this one's got a door that you pass back through. Those are the hops that are really important to keep track of. So here's kind of where I'm going. This is what I mean about text. So that when I was talking about the BGP, this structure right here is kind of what BGP pushes out. And I said earlier, there's a structure to how you group IPs. This is what they call a /23, which is a certain range of IPs. I don't want to go into more detail than that right now, but they all belong to this particular AS. And you know that because it's the farthest right number. And it's telling you that a valid path for this block of IPs is to go from this block to this block to 3257 and then 1239. If you look right here, it ends. And if something from 1239 wants to get out, it may have to take this path to get to here. The second line does something similar. It starts here, goes through 2115. As you can see, I'm doing it right here. Hopefully you can see my cursor. Then it goes to 3257. Then it goes to 1299. And then it goes to the 6762. And it may transit back the same way. I didn't try to depict them all, but key thing is like, this is a terminus. This ends. So if I'm in 7018, I automatically have to go here no matter what I do. Is that
And
clear
these
to
are-
everybody? Go ahead.
These are set up, these are just set up because, or through BGP, right? Through
Yeah, this is how BGP talks. And this graphic is not the whole internet, obviously. Past
Right.
AS174, there are more connections. What I can tell you is there's no more connections right here. It tells me it terminated.
But depending on how the way that you are putting it, it sounds like it's like constantly evolving and morphing, right?
Yes.
So something like this, even though it's a terminus right now, depending on certain factors, could
Change.
become a link in the chain. Okay.
Yeah, it could change, but it won't be arbitrary change.
No.
For example, the reason these all terminate for 7843 is 7843 owns all these IPs that are being routed here, but they sold it or leased it to another AS. So they have what they call tier 1, tier 2, and tier 3 providers. And I always caveat this, do not think internet connection. Oh, I've got a T3 internet connection. I'm not talking about that anymore. And I'm talking about physical topology here. It's one of those reasons why I don't put it on the slides and I hesitate to bring up, but those providers like your RARs, those regional internet registries, they're tier 1 providers. Between all of them, they have the whole internet that they're responsible for. And they lease that out to very large ASs. So this, this particular AS might be enormous. It's not, but it could be. But all of these are descendants of, if you will, because past 11427, there's another AS. It's just not on the diagram because it's not critical. At some point, though, each one of these has a beginning AS where it has a descendant. So I want you to think of this as hierarchy. So this AS right here, 7818, somebody purchased from 7843 all the IPs that are in this bucket. They could quit paying and those would return here. And our BGP and our AS numbering system would shift to accommodate that. They could then resell that and make a new number, right? This AS 6461 could sell off a chunk and create a new AS. That's how it changes.
Okay.
But you won't just have one show up out here, out of thing, nowhere. Everybody is a child of somebody else now. So you can watch for that. And you can learn insights from that. You know, like a criminal rarely owns an AS. Nations own ASs, large organizations own ASs. They're very hard to hijack without being caught. I'm not saying you can't, there's ways to hijack anything, but you're not going to just take over an AS that's kind of hanging around. It does not work that way. They have insane amounts of insight and control. Because one of the questions I expected back on that slide of like, who owns these ASs was, do governments, do nations, like who manages this whole process? Well, if you look up IANA, they're not a country, they're an organization. But look how much control they have over the internet. They can make decisions about ASs and who can sell them and so on without regard to any country's laws or politics. And that's kind of important. I'm not saying they're not influenced by key organizations and countries, because they are, but they are independent from them as well. And it's sort of like how the Federal Reserve in the United States is independent from the government. It's that kind of relationship. If you're not familiar with why that's important, that's a separate conversation, but we should have it. Or you can look it up. But staying on topic, the question of what does it look like? It looks like this. This text blob is exactly what came out of BGP. I pulled it last night. And the structure is from a looking glass that gives you insight into things. All right, so why do we care? I mean, why do we give a darn about this? So here's my icons. I told you I'd put the analyst piece, actions artifact, and the fact that someone's leaving a trail or doing something. Part of this first statement is really critical. The internet is three and four dimensional. So too many people as analysts in our field look at the internet like it's a flat 2D space. There's an IP, and if they look at a blacklist or they look at a couple of tools online and don't see any bad things, they think that it's okay. And they forget that there's a lot of intelligence and analysis that can be done on just knowing where that IP is positioned in relation to them. Hence the 3D, 4D space. You know, the 3D space is just figuring out positioning between you and the, say, where the command and control was or the attacker was for whatever hurt you. And the 4D space might also take into accommodation the pathways, as well as the actions that were took for that path to actually be created and followed. And so it's really critical to keep these in mind. You're better analyst if you understand this, because then when you query something, you see a command and control for a piece of malware that got in your environment, and you look it up and you're like, oh, it's that data center in Vietnam. Okay, if it's there, then I know it had to go through. And you can start back tracing all the name servers that did the handoff, which is another part of DNS. If you remember that those things sit at a lot of the gateways, and you can kind of get the hops that it had to take and then understand what path. And then you can go to, in some cases, if you're a entity that has the ability to do so, query those and get even more data for your investigation. It's kind of, your limitations are only by what you can imagine and what you have access to or can get access to. And secondly, I already covered the second bullet, I'll pass that. But the last one there about logical groupings and patterns of behavior, some things will stand out depending on how everything is structured, like their IP in relation to yours, so their computer in relation to yours, their jump box or the location which they attack from in relation to you, in relation to them. All those things become elements of analysis. And it's why we care about how DNS is constructed. And I promised I'd put a very ugly diagram up. I didn't tell you that part, but I'm doing it. That talks about some things. So those autonomous systems are in the middle here. And there's three major things you can absolutely glean or do in relation to this. You know, and there's questions the attacker asks, and there's questions the analyst asks. So routing changes is that concept of, can I, attackers like, hey, can I hijack this route? So there's a type of hosting that criminals use, Bulletproof Hosting, which is a promise from another organization that's either towing the line of being legal or absolutely not legal at all, that says, hey, I can make sure that whatever you're doing is always online. And many of them exist by stealing IP ranges and routing from ASs that do not watch their routing tables. I'm sure you can imagine that there's plenty of companies out there that are like, it's too expensive, or I don't have the time to pay attention to this thing. And so they're able to take advantage of that. And so they hijack. They will figure out a way to inject themselves in the BGP protocol and announce a route that is not true. If you remember earlier, I said every AS announces to all its neighbors the routes that it handles, right or wrong. There was an incident that happened, I don't know, 5 years ago, 6 years ago now, where an ISP in India said, we don't want to allow YouTube to any of our subscribers because there's a reason. I'll get into, I mean, basically their government said, don't allow that. They had a reason for it. And so they said, nope, we're not routing for that. So they chose to reroute any requests that out of their AS that went to any YouTube service. They're like, nope, we're going to reroute them somewhere else. But they forgot, and they did not keep that local to their AS. They let it get announced to all their neighbors. So guess what all their neighbors did? They picked up that routing change, and then they quit routing it, and their neighbors quit routing it. And within about an hour, they took out about a quarter of the internet's ability to route and get to YouTube. It took less than an hour. Now, it took about 6 times that to fix it. And part of the way that it got fixed was the ones that are attentive figured it out quickly and made changes. The ones that the owners, all the way back to IANA and the regional registries, they said, fix it. And for the people that did not listen, they quit routing for them completely, which is the stick that they wield. So if you remember, as another story that's related to routing, Cogent, which handles about 25% of the internet in the world, is a very large company that decided because of Russia's actions invading Ukraine, they were not going to route traffic to ASs that existed and were in the hands of the Russian country, the government. And as you can imagine, that's a huge impact because now they're forced to take a different path if they want to get routed. And that slows them down significantly. These are kind of the decisions that routing changes can kind of impact. And there's other things. There's lots of espionage ways where countries have announced routes that don't exist in order to take up traffic. Cyber criminals even broke into one AS and it was a specific AS that they targeted because it was connected to and managed a lot of a cryptocurrency trading organization online. A lot of their traffic and their pools where people were mining for Bitcoin and Monero and other things was transiting that AS. So they announced routing changes so that all that routing went to them instead. And I think they collected around $100 million or so in cryptocurrency before they got shut down. So it's not, it's not for the faint of heart, but you can have a big payout or have a big effect if you really want to. That's not the only thing. But so a couple things you can do there. Of course, you can hijack it for financial reasons or to do espionage. And then these bulletproof host providers, they announce in order to have IP space that's normally either not announced for or is just abandoned or not cared for, so they can have people hosted there. So every AS, as an example why that works, may have, say, 10,000 IPs in it, but they won't announce for all of them simultaneously. Usually there's a darkened space or a chunk of IPs that are not being announced for on purpose. They're in reserve in case they need them for any kind of surge activity, and they may also be allocated against a future need. And so as a bulletproof host provider, I might come in and cut away like 12 of those, and you may not even notice. It's that kind of activity. The other part is man in the middle, which is exactly what it sounds like. It's the telephone game of sorts. Somebody's going to sit in the middle instead of being mean in the telephone game and not understanding you and kind of passing it on. They're going to just sit there and intercept it, and they're going to snoop on what's there. So they're eavesdropping. You can do that, like I said, if you understand where the choke points are, either force people to them or make that, or just look for natural ones and then observe what's happening. So the attacker says, can I hijack this? The analyst says, is the route correct or has it been hijacked? When they're snooping, they ask, can I snoop on things? And then the analyst is like, hey, is somebody intercepting our traffic? I've worked for companies who've had that question, is somebody intercepting our traffic? Sometimes it's true, most of the times it's not. It just depends. This is man in the middle action at a BGP level is usually something countries do or large organizations do more than anybody else. I'll skip those stories right now. They're kind of tricky to get into without getting into too many details, but we can talk offline about that. The out of place traffic, the attacker, when I was talking about data centers and stuff earlier, the attacker always asks, hey, can I hide here? Can I do actions here that won't get detected or won't get shut down? It's always that case. Now, they don't think about BGP a lot of times when they're acting. I'd say 99% of them don't even consider it at all, which is why some detections become very easy when you understand that. Because we're like, hey, does what I see match a pattern that I'm looking for? And nothing stands out more than out of place traffic. So if I, as an attacker, grab a chunk of IPs in residential space and I start acting like I'm a data center, I tend to stand out. Hopefully, you know or can conceive that traffic coming from your house is wildly different from traffic that's coming out of a data center. Because what do you have in a data center? Anybody? What kind of service would you have in a data center?
You could host servers for people who want to rent out like video game hardware.
Sure, absolutely. You might have that. You might have databases, right? You might have someone with a website. You might have e-commerce. You may have just some kind of system that's fielding content back out. So the amount of traffic coming out of there, leaving that AS that owns that data center, the way it is logically set up, is going to look wildly different than, say, a neighborhood that's being served by Comcast. The traffic coming out of there is going to have a completely different pattern. So when a large chunk of IPs or even a small chunk start doing weird things that resemble another entity, they're out of place. It's one of the easiest kinds of analysis you can do. Right? It's kind of a form of A/B analysis. You're looking at A and B and seeing what's different. And we do this often, very, very often. And this is the simplistic kind of explanation of that. There's lots of ways to use that out of place thinking to look for things. In this particular case, I'm looking for traffic that normally, say, selects a certain path, but all of a sudden is now taking a completely different path. And that might be because one of those ASs in its chain refuses to pass on anything that looks like malware, in which case it would force it to take a different path. It's one of those fun ways you can use BGP and AS understanding to find malicious activity, for example, or someone attacking you. Okay, one more example, then I'll go to questions. I can be in my house and be on one IP address, which puts me in one AS. And then I might go, hey, I want to be safe, so I buy a virtual private network, which is a fancy way to say that from my house, I'm going to have my IP connect to another IP somewhere else in any part. Let's say I connect to, somebody give me a country.
Sumatra.
I connect to Sumatra. There's a VPN setup that has Sumatra on there. And now when I search the internet, it looks like I'm coming out of Sumatra. Now that means that my computer is constantly connected to the Sumatra server in this case. And from there, I do my browsing. So my AS has to route and connect to that Sumatran AS, which will then route and connect to wherever I'm trying to go. And it'll come back. If you're in the middle of that, you can see that whole path. You'd have to be really in the middle between your residence and your Sumatran VPN, because that's where the Sumatran server is. So conceptually, you can figure that out. Now, if I interacted with someone's website and they were trying to trace me back, it would usually stop at the Sumatran server, because that's where I'm going to, for all intents and purposes, navigate from. But the minute you download a file and do something on that file that goes back to the internet, now you give away your position. Your VPN is useless at that point.
Ooh.
That's why I'm always harping on other analysts. Be careful what you pull down, and be careful what else you have ongoing on your computer. So if you're logged into social media and other things like that in the same computer that you're doing this kind of research, even if you're on a VPN, you give away your presence and your internal IPs, like where you're actually coming from. Now, if we can do it, I want you to, hopefully you can understand that the attackers also fall for this particular problem. And it's very normal for them to forget they're logged into Facebook, they got their email open or something else on the same computer that they're trying to access and be anonymous with. And it can be a giveaway. All right. I'm teasing for the future. Big question mark. What do we got? Dead silence. So, no questions is good.
There's a lot.
Yes.
One question I had, you mentioned earlier for the hops, and that every single hop that a piece of information takes is automatically recorded
In the packet.
and it's built into that whole system that they
Yep.
record the hops that they take.
Yep. Every packet is what it's called, that bundle of data.
Mhm.
And it uses a TCP IP format, which we'll get into later.
Mhm.
One of those things in there is the idea of hop count. It wants to know how many servers it had to transit. So every time it hits a router, or every time it hits an edge of something, it flips that toggle to +1.
And then my question is though, you mentioned that you could squish them. You can step on them or you can
Sure.
mess with them.
You can overwrite it. So it's a common thing that defensive security tools look at is hop count. Now they measure it inside networks mostly to understand how many hops it took for like my computer to get to a SharePoint location. And generally that's under 7, frequently less, sometimes it's under 3. It depends how tight your network is set up. And that's important because if you have someone who's consistently, doing 10 or 12 or 15 hops, there's a misconfiguration somewhere, or there's a problem. That's one of the ways that they use hops for diagnostic reasons. But you can have a defensive tool that says, look, any hop in our network that tries to go past 7 dies. We just kill it immediately. That's one way you can prevent data from leaving your network. Because remember what I just talked about. I'm a bad guy. I'm on my laptop. I connect to my VPN. Hop 1 from my computer to the VPN to you to where I'm going. And then I start to go backwards. I might exceed that limit of 7 before I even try to exit the network, and it's going to drop the packet. That's one way you can defensively keep somebody from exfiltrating data. Most of the next generation firewalls and a majority of the what we call EDR tools, which endpoint detection and response is what that stands for, they look for hop count and they act on it. They all just kind of do it a little bit different. Their thinking and logic is slightly different. But the core of that is when hop counts get over a certain amount, it doesn't allow it. Now, I'm going to tell you 2 things that are going to make you really get frustrated. Linux says any hop count that goes over 15, by default, it indicates that it should drop the packet. It's kind of a core thing built into Linux. And depending on the flavor of Linux you have, that the distro, if you will, distribution, that may change a little bit. Windows pretty much allows up to 100 hop counts before it says something's bad. So you can't rely on them for those kind of things. That's why there are tools, security tools that kind of go, no, we've measured our network. It should be much smaller than that. Because 100 counts will get you around the internet a couple of times and back. That's kind of insane, but it's a redundancy thing.
Okay.
Okay. So my takeaway for you is remember, as we continue to talk about this, well, we'll loop back to these because they're an important part of analysis. When we talk about how to draw what we call constellation, which is how this is all connected, you'll see why this really becomes critical and how you can use it in ways to understand and stop adversarial action, which is kind of what we do as a defensive analyst, or find what's going on if you're a research-based one, talking about our first slide decks. But big concepts. Don't forget them, even after you forget about the slide deck and you're 4 years in the future and you're looking at a bunch of IP addresses, wondering what's going on. Remember, follow their clusters of IPs and who they belong to all the way up to the AS and understand how they interacted with you so that you can get a bigger picture and understand overall better what's going on. That way you can give good advice. All right, I'm going to stop the recording unless there's any other questions. I'm going to take that as a no. All right, recording has stopped. You can all cuss now.
Wait, it still says recording on the top.
What?